Thank you for joining the hands-on workshop, Performance Optimization for Intel Xeon 5 Processors. This is episode number 8. I'm Andrei Vladimirov with Colfax International. In this episode, I will talk about performance tuning with Intel Math Kernel library. Intel Math Kernel Library, or for short MKL, is a library of standard mathematical functions that are optimized for Intel architecture processors, including Xeon and Xeon Phi, first generation and second generation. In MKL, you will find support for linear algebra and fast Fourier transforms. These are the most frequently used modules of MKL. Linear algebra support includes BLAS, basic linear algebra subroutines, LAPACK, linear algebra package, sparse solvers, and others. Fast Fourier transform is available for one-dimensional and multi-dimensional transforms, as well as cluster implementations. There are other modules of MKL that you might find useful, such as random number generators. Some of them can be used in multi-threaded contexts, vector math, summary statistics, data fitting, and module that's currently in production, which is deep learning primitives in MKL. I will talk today about making decisions on parallelism with math kernel library functions. Many MKL functions are multi-threaded. So when you have the task of batch processing, where you have multiple data sets for which you need to run an MKL function, the most obvious option for multi-threading is just to call an MKL function and expect it to have multi-threading inside. When you are done with this dataset, all of your threads move to the next dataset. You're done with this dataset, all of your threads move to the next dataset. Again, all you need to do for that is just call MKL functions one by one. If you have multiple datasets, another approach is to put only one thread on each and process many datasets at once. These approaches have advantages and disadvantages. In the first approach, the advantage is that at any given time you are working on a small amount of data. So potentially you are staying local in memory. But the disadvantage is that your dataset may not be large enough for all of the available threads to really contribute to performance in a meaningful way. In other words, you may not have enough parallelism in one dataset. With this coarse-grained parallelism, where you process multiple datasets at once, the advantage is that if you have many datasets, potentially you expose more parallelism. But the disadvantage is that you have to keep multiple datasets in caches at the same time, which means that your data locality may be degraded. And of course, there could be a sweet spot between these two approaches, where you assign a group of threads to each dataset, and when you are done with one dataset, this group of threads moves on to the next one. This allows you to find the sweet spot. You can try to find the sweet spot with nested parallelism, and this will require some tuning. But for some functions, MKL also has support for batch mode transforms. So this is what I'm going to demonstrate today. For this example, I will use a calculation that performs fast Fourier transforms on multiple relatively small arrays. Specifically, I will transform arrays of size 2048, and I will have a lot of arrays, something like hundreds of thousands. Switching to my server with a Knights Landing processor. If you have not watched earlier episodes, here is a demo. This is an Intel Xeon 5 processor, 7210, with 64 cores at 1.3 gigahertz, and this is one of the systems from dap.xeonphi.com. The code that I have takes the FFT size from the command line, and I will set it equal to 2048. Also from the command line, it takes the number of transforms that I have to transform at once, and I will set it to 200,000. Then it allocates a large array to keep this many transforms of that size. The data type is MKL complex 16, which is double precision complex numbers. Here I initialize the discrete Fourier transform interface. I create a handle, which is a descriptor of the transform. I say that it is going to be a double precision complex to complex transform, one transform at a time of this size. And then I also set a parameter that indicates that this transform is going to run in place. I initialize my data, and then I go and do my benchmark. I will do several trials, and in each trial I will loop over all of my data sets. So this is the loop that contains 200,000 iterations. And for each data set, I will call the MKL function, and there is going to be multi-threading inside. Let's see how well this works. To compile my code, I can simply run Intel C++ compiler. Here's the output file name, app, and I want to compile it with support for the math kernel library. That's all I need to do. And now let's run it. It requires that I specify the size of the transforms and also the number of them. So I will run app, FFT size 2048, number of transforms 200,000. Here it is running, and while it is running, let's create a log file. So my first code is fine-grained parallelism, meaning that in this scenario I do the following. I put all threads on one dataset. When they are done, all threads go to the next dataset. Well, let's see how my calculation is doing. So here it is computing, and for trial 1 the performance was 4.8 gigaflops per second, trial 2 4.9, and so on. Well, while it's running, I think I can safely average this to 4.9 gigaflops per second. So let's try another approach. Let's try the coarse-grained approach. This is where we are going to put one thread on each dataset, but process multiple of them at once, many of them at once. This is how I'm going to do this. In my code for this loop, I will simply put pragma OMP parallel 4. What it's going to do is it will create multiple threads and distribute these iterations between them. Thankfully, the data for all iterations is independent, and handle is a read-only object. So I will call from each thread the FTI compute forward. By default, nested parallelism is forbidden in OpenMP. So automatically, I will have single-threaded implementations of MKL fast Fourier transforms inside this loop. So I just made one change, and let's see what that did. So recompiling. MKL uses OpenMP behind the scenes, but now I'm using OpenMP explicitly in my code, so I need to tell the compiler about it. Because I'm explicitly using OpenMP, I need to include the flag QOpenMP, and I need to link to the math kernel library. And here is the source file name. And while it is running, let's take a look at what's going to happen. The number of elements in each of my transforms is 2048, but the number of data sets is 200,000. In my Xeon Phi processor, I have 64 cores. Clearly, this number is smaller than the size of one dataset, but it is getting uncomfortably large relative to it, whereas compared to the 200,000, this is a small number. So potentially I will expose more parallelism when I do one thread per dataset. So let's see how my application is doing. It has finished, and now I'm measuring 72 gigaflops per second. Not bad for one line of code change. But my idea of the best scenario is to allow MKL to figure out how it wants to do parallelism, and for that I will use the batch functionality of MKL processing. To change my code to batch processing, I'll need to get rid of the loop, and I will only feed the entire data set. This is how I want to do this. But before I can do that, I need to modify my descriptor. Specifically, I need to indicate that I'm going to run several transforms at a time. And this is how I'm going to do this. dfti set value sets the value of one of the arguments of the descriptor. The argument that I want to set is dfti number of transforms, and this number is equal to num fft, in my case 200,000. And I also need to indicate how these transforms are packed into the single large array that I'm going to pass. So I need to specify dfti input distance, and they are packed this many elements apart. So I will set this to fft size, and the same for output distance. Importantly, I no longer do anything with loops, I don't do anything with threads, I just pass a batch into MKL. Let's recompile and rerun. It takes a little while to initialize, so I will go and prepare the log. So batch processing. And I probably need more space. So it's still initializing the dataset. I think it's doing it with a single thread, so it takes a while. Oh, there we go. The results have come in, and I am observing 113 gigaflops per second. This is not bad for no work except specifying how exactly I want to process the multiple datasets. In my slides, I have a cheat sheet illustrating what exactly I did here. There is one more room for optimization, and that comes in the optimization of data containers. How do I allocate my container? I simply call the malloc function, asking to allocate this many bytes, and then I pack my data in there. This could be bad for several reasons. One of them, poor alignment, and the other one, missing some other interesting opportunities. So let me see how I will improve my results by just changing my container. Instead of malloc, I will call mkl malloc. This is one change. And the other change is that now that I'm using this other allocator, I have to specify one more argument. And this argument is alignment. So let's see what this does. And again, it might take a while to initialize, so I'm going to go and prepare my log. And let's see what happens. Well, this is certainly a very different result. 383 gigaflops per second. So this is a pretty impressive improvement. By just changing the allocator, I gained more than 3x in performance. And there is an interesting detail in what happened. Turns out that MKL, behind the scenes, used the high bandwidth memory. To prove this to you, I will make my calculation run slightly longer. Let's recompile, rerun. And while it is running, I will make a note of the process ID. And the process ID seems to be 106367. And I will run numastat -p followed by the process ID. So my calculation is running, and as it is running, I can see the utilization. Memory utilization is broken down by nodes, node 0 and node 1, and these are my NUMA nodes. You can see that most of the memory is allocated in NUMA node 1. As a reminder, NUMA node 1 is my high bandwidth memory. So once again, while this calculation is running, here is the memory utilization. I summarized my performance measurements, including the one with the modified allocator, in this plot. And I'm showing the red bars for the same system that I've just experimented with, and this was my initial code. Then I show the result for the batch mode and the result with improved allocator. There's also performance results for a CPU and for a first generation Xeon Phi processor. And you can see that there's two additional performance tuning steps: affinity tuning and parallel first touch. You will notice that these two additional steps made no difference on Xeon Phi. That is because performance on Xeon Phi was good to begin with. But these steps made certainly significant difference for the CPU. In this sense, it looks once again like the Knights Landing processor is slightly easier to program than a Xeon. This concludes episode 8. And in the next episode, I will talk about machine learning on Intel architecture, including Intel Xeon Phi processors. See you there!